Hello everyone. So welcome back to the week 5 of this course, and let us pick up from where we left last time. So what we were discussing last time when we met was that we were talking about demand side management, and when we started talking about the issue of demand side management, we were talking that why the demand side management issue is becoming tougher as or maybe more complex. Tougher is the wrong word, maybe more complex with renewable energy coming into picture. And with renewable energy coming into picture, we were talking then for a phenomena called duck curve. It is being observed, specifically this kind of analysis started in California, and now many places in the world have started following this kind of analysis, that we see that when the renewable energy generation starts, so the net demand from the grid side start taking a very peculiar kind of a shape, which can be looked as kind of a duck curve. So in the daytime, the demand can almost look like a belly of the duck, and it means more and more energy is being consumed through renewable energy generation sources only, and that would in turn mean that the grid dependence in the daytime or the time when the renewable energy sources are utilized. Specifically, this is done for solar cell right now, more with solar cell, because solar cell specifically has a very peculiar behavior that it kind of gives output in the daytime, and it doesn't give output in the evening times or the morning times or night times at all. So when then starts happening, so the requirement from the grid side reduces significantly, but that it can create an impact on the grid reliability, because suddenly the ramp up required from the grid would be much sharper. Grid would need to produce much lesser in the daytime when this renewable energy source or the solar energy source is available. So the problem with that is that suddenly regular sources of power generation has to be reduced drastically, and then it has to be ramped up again in the evening when the power requirement is there. So this is what we were discussing last time, and then we said that okay, we will start looking into issues that how it can be handled, and overall how DSM can actually be used as a tool for energy efficiency, or maybe how can it compensate, or how it can be a complementary effects along with the energy efficiency as a concept. So for flattening the duck curve, there are multiple aspects which has been kind of worked out. One is from a supply side response is that what is being done is that when you have excess generation of energy, when you don't want your grid to go below a certain level of supply, so it means if renewable energy is still generating, what will happen is that suppose you have renewable energy generation at that time, while the uses of renewable energy is only this much, if you start using renewable energy beyond this point, it will start fattening the belly of the duck. So that would mean instability of the grid side or a faster ramp up in the evening. So for that, what is done is that extra energy is kind of stored somewhere else during this time and utilized at a later part of the day. So suppose this is your kind of consumption, and you're generating renewable energy like this. So what you are doing is that this excess energy which you are generating in the daytime is you can store it in an appropriate storage medium, and then you can utilize some other part of the day. So that's what the whole research is going around batteries or pumped hydro storage, and we'll talk about that when we go to on the generation side of it. So that is one way that how it is being compensated, or this issue is being handled. Second issue is being handled is that people are trying to see that if we can make this renewable energy generation more flexible and dispatchable. So for example, in California, what very interesting experiment was tried after seeing this behavior, that subsidies which were given for the daytime generation were reduced. And it was said that the subsidies would be given for if people are willing to put their solar panels more towards west facing side. So as we can see that around the evening, the requirement kind of ramps up very quickly. So what was said that instead of having a solar cell generation which is very sharp peaked around the center period, can we broaden this peak also? Can we broaden that by installing solar panels which is west facing, as the sun kind of sets in the west? So southwest kind of installation of solar panels will ensure some kind of higher generation in the evening period. So that will kind of shift the generation side and kind of broaden the generation peak. So that is another experiment which was tried there. Then things were also are also being tried from the demand side response also. So incentives sometimes are given for shifting consumption to more solar hours. So tariffs are reduced, or sometimes the models are created in which people are incentivized to use more energy or maybe shift their load from some peak hour is happening in evening sometime. So they're incentivized to shift the load when the generation from renewable energy sources or solar energy sources is happening. So that kind of reduces the higher power requirement in the evening. So lesser grid power requirement, lesser grid infrastructure requirement, lesser net energy generation which will be needed from fossil fuel based sources. So overall demand is reduced at when they expect peak to occur, and it is people are incentivized to shift their demand to the hours when the renewable energy generation is taking place. So that's how people are working to reduce the evening demand peaks on this. So overall DSM kind of focuses on demand as a flexible kind of a resource. So if you can then start playing with the demand side of the equation, you can start creating some kind of flexibility in the system design itself by monitoring not only the generation side but playing more on the demand side. So it's kind of an indirect way of handling the energy consumption reduction, or not consumption reduction per se, but kind of infrastructure load reduction is what can be worked out through this mean. So just to kind of give an overall view of that, overall DSM can work on a power system in multiple ways. It could be economic, that it could lead to extra capital cost avoidance. Overall efficiency can improve because we can more efficiencies of the system can be improved because since the transmission will be lower, so I square R losses will be lower, so heat losses will be lower. We can design systems which are much more resilient. This can also lead to a premature aging reduction also because the stress on the systems will be lesser. Customer side also there could be some bill cost reduction because customers are incentivized to use power during the period where the peak demand is lesser. So if you can have a dynamic billing system, and if you can have billing depending upon the load on the grid, so by having this dynamic billing system, customers are then incentivized to use more power in the off peak hours, and that's how they can overall reduce their billing hours. So I know a couple of industries. This thing is being tried at an industry level in state of Uttar Pradesh where I teach right now, where more nighttime tariffs for some of the industrial areas are lesser compared to daytime tariffs because in day the grid load is higher. So some of the industries have moved some of their energy intensive efforts to night shifts, so that energy intensive operations they have moved it to night time, so that they do those operations in the night time, so that way they can avoid the higher tariffs levied on them during the day period, right? On the technical side, overall, as you can understand, it will lead to overall reliable system. It can work to improve power factor. It can lead to extended facility lifetime. So there's multiple aspects in which the DSM overall can work as a very good strategy, and that's why this is a highly studied field these days. That how DSM can be rightly integrated in the overall power management system to start helping the system to reduce the overall burden on the grid side, and also how overall it can be worked to reduce the carbon footprinting of the system also. From an environmental side, of course, it will mean lesser environmental damage because carbon emission can be reduced, because then you don't need to create unnecessary infrastructure. The power demand also since it doesn't peak, so the overall power it has been worked out that overall power consumption also reduces indirectly. It improves customer satisfaction because customer is then getting more reliable power, because then the tripping when the load goes to maximum, there were earlier issues of tripping of power which can happen if you don't do this demand side management, so that tripping also can be reduced. For market side, it could lead to lesser price volatility. Market power mitigation also can be much better. It works on risk management improvement also. So overall, it's a very interesting phenomena, kind of economic phenomena which can be worked out to reduce overall stress on the system and work for a more reliable power system. If you go into core categories of DSM, demand side management, and how it can work, so we can broadly categorize into three parts. One on the energy efficiency side, where we can talk about permanent reduction in energy uses. I'll come to all these three issues in next couple of slides. It can work from the load management side also, that how changes when energy is used. I have kind of touched upon this point slightly when I was talking about the renewable energy side management when I was talking about DACA, but I will kind of make 1 or 2 points more on that in a couple of slides. And then there's a demand side response, the short-term demand adjustment during the system stress also can be looked at DSM. So let's look at all these three aspects. So from the energy efficiency side, what can be done is that overall people can be incentivized to use more efficient appliances motors, lighting, or industrial process, wherever we are seeing that there is a stress on the system, stress on the system is coming from higher demand because of the some devices which are being used at a specific hours. For example, if I'll come to agriculture sector in few more slides. So suppose a specific village, it is pumping the water at a specific hour, and then what it leads to is that since multiple motors might be working at the same hour, so they will can all add up and can have a sudden peaking of the power demand at a specific time of the day, and it is water table dependent. That cannot be avoided. So what can be done is that can we start using more efficient motors, and so that it kind of reduces the overall power demand at that point. Similarly for lighting, for industrial processes, for each of these things we can start looking at this. What is leading to that peak formation? Is it the consumption, or is it because of the inefficient devices? And if it is because of inefficient devices, can we work on the devices side to reduce overall energy consumption for that particular hour, and we can reduce the peak overall. It can lead to long-term reduction in energy consumption, because obviously once the more efficient systems are being put in, it will lead to a situation where the overall electricity consumption can come down. Often reduces peak demand as a secondary benefit, of course, because that's what we are talking about, that you can call it secondary or you can call it as a primary benefit, but this is all what is worked out, is that it is all worked around reducing the peak demand. And it has effects on its structural, and it is more persistent as a method, because now what you are doing here is that you are making a change which is more permanent in nature. So that permanency of this change is a very effective way of doing this management. Second thing is that what I kind of mentioned earlier was about with respect to load management. Remember when I was talking to you about renewable energy and duck curve and issue like that, I was talking about incentivizing people to use more devices during the daytime, so that your overall load can be shifted from peak hours to daytime generation thing. So that's where people can start using more devices if they can be incentivized. But why only that? What we can also do is that overall, wherever we are seeing the peak coming in, can we work in terms of incentivizing people of not using their devices during the or incentivize people to use devices during the off-peak hours, or work out some methodology of reducing this clip of peak clipping is something what we should, what strategies can be built around. I know Delhi Discom or some other Discoms also have been trying to work out this model. It is not so easy, but people have been trying to work out some models around it. And what is the overall idea is to clip off the peak and fill up the valley. So you want your power consumption curve, if it is having a shape like this, for example, what you really want is that you want this peak to kind of get clipped, and you want you want to fill up these valleys. So overall your power consumption curve should look more like this. So it kind of systems become more resilient. The variations in the systems are lesser. So with the variations being lesser, the overall system reliability works much better. So this is something which is worked out as a strategy at a lot of places. Third one is that you kind of work on the demand response side, where you overall you say that we work towards that, can we work on the demand itself, and we can give some price signals, we can avoid some grid congestions through this route. It will also help us to avoid some supply shortages. Since these two are disadvantages to the system right now, to handle this issue, can we give some price signal to the market, that by giving that price signal to the market, can we incentivize market to shift their demand overall, so that we can avoid these grid congestion issues and supply shortage issue. So it kind of provides that operational flexibility during the critical period, and that it leads to overall grid stability. And so since we are talking with respect to carbon, you can imagine, since my peak will shave off. So currently the systems are being designed to handle this peak power, and if I can shave off the peak, then I need to design my system only to this much. So if I just putting a number, that if you need to make a 2 gigawatt kind of a plant, maybe you are good enough to work with 1.2 or 1.3 gigawatt plant itself would be good enough for you to handle that kind of a load, if you can work on very good demand side management strategy. Another method which is being talked about is price based demand response, that consumer are given a time varying kind of electricity prices, and again for that what I mentioned is that smart meters are the ways through which it can be handled. So we can work on time of use tariffs, we can work on critical peak pricing, we can work on real time pricing. So this is again a model which is being worked out, and as many countries who have already made this transition, specifically some of the mature economies who has already made this transition, are already working to have this smart metering phenomena, and they the user gets a message from the utility that using the power during this specific hour will lead to higher tariff or lower tariff, and that's how the, so for example, if you're an office goer and you know the power cost will be lower from 12 to 2, I'm just putting a number, but you're not at home, but can you then program your washing machine to operate during that hour itself, so that you are not consuming washing machine power during the period when the electricity prices are higher? So suppose you are at home at morning and evening and electricity prices are higher in morning and evening, so rather than using your washing machine at that time, can you then work out a program based washing machine where you operated from 12 to 2, or you operated in midnight, wherever the tariffs are the lowest? So that's how you kind of work out. Even for air conditions also, sometime you know that in evening, by the time you reach home, the power tariffs will be higher. So can you switch on your AC during the daytime when the power tariffs are lower, and cool down your house to a certain degree, so that in the evening when the prices are higher, you don't need to start from a very hot house to start cooling your house, rather than you have a kind of a stable house at that time, and through which you can then use lesser power and then cool down your house much faster. So there are multiple price based demand response strategies which are also being worked around that thing. Another thing could be incentive based demand response also, that utilities can directly incentivize or control certain loads, and which can include direct load control, curtailable contracts, demand bidding. So utilities can kind of force their user to that if they use, or if peak is coming during a specific period, they will be suddenly charged higher. So that kind of triggers a behavioral change in users, where users starts not go beyond a certain kind of a connected load, and they kind of work much more disciplined way to consume power when utilities want them to consume. So because this would otherwise they will be charged higher, then there could be penalties, there could be some fixed charges increase, which all can lead to this such a change that behavior. Utilities can use that as a instrument to change this behavior of people. It is much more predictable because utilities are controlling it. It is not controlled by the user themselves, but it requires strong institutional capacity, because then utilities needs to have that kind of a control on their grid, control on the metering system that they have installed, control on overall monitoring of the system. So the multiple institutional capacities or capabilities has to be established if utilities have to really work on this aspect from a perspective. In India also, this DSM in power system is being tried. So India experiences sharp power rise in the evening hours, as is visible here. India have this sharp peak rises in the evening time, and also at the same time India is growing very quickly in the energy consumption side, because half of the India was unlit for, not many years back. Or major part of the India was unlit not many years back. So as India is getting connected, people are having more dispensable income. So overall energy consumption for India, which is much lower compared to the world average even today, that is on an increasing trend. And with this increasing, electricity consumption is overall increasing. So this is another thing which is happening. And if we are not careful on managing our demand side so much, so what it can lead to is that it can certainly lead to a situation where the peak demand during peak hours that can very sharply rise, and that can lead to situations where we can again start having issues of power tripping and having issues of grid instability. Not many years back, many of you will remember that we used to have this very frequent issues of specifically in tier 2 and tier 3 cities, where used to have very low voltage coming because the system was overloaded. So which has been reduced drastically through the higher generation, and since India is sitting on a positive generation right now. But if we don't control our growth, if we don't have the demand side control in a structured way, this can again lead to a situation where we will start again getting those kind of power cuts. We can start leading to a situation where, because either the infrastructure has to keep its pace with the increased demand, and that too specifically peak demands whenever the peak is occurring. And if we are not careful of controlling that peak demand, we can lead to a situation where we can overall have a situation of power cuts and unstable grid again. So DSM is a very good strategy that can help to reduce cost and improve reliability of overall system, and that's why many Indian companies and even Indian government also is looking at this as a tool to work more and more. Let's talk specifically about some sectors, as I mentioned a few slides back. If you look at agriculture, agriculture contributes significantly to peak demands in many states. What happens is that people are using pump sets. There are specific issues where villagers use pump specific covers depending upon their agriculture needs and stuff like that. So things are being worked on efficient pump set. When I come to generation, I'll talk about off-grid solar cell pump sets also. But as you might have already heard about it, that is being talked about, and under a PM Kusum Yojana that people are talking about, that this is specific off-grid pump sets which are more solar cell based pump sets. So, but before that also efficient pump set has been a discussion topic for many years, and this is being pushed into system more and more. Feeders are separated so that this specific peak doesn't load overall the system, but specific feeders. So this feeder separation is another method which is being deployed for this thing. Time control electricity supply is also something which is being pushed into the system. But more and more what government is pushing for is that if they can somehow bring many of these pumps on off-grid mode, then this will reduce this unreliability to the grid which is happening. But obviously this has its downside also, as maybe during this course somewhere down the line I'll talk about this issue. But this has a downside issue that now electricity might be available on a click of the button, which is stressing the water table. So that is another downside issue of such a scheme. But coming back to electricity side, this is something which is being tried. On the municipal DSM side, the issues are street lighting, water pumping, municipality building itself, consumption from them. So many public services are being targeted. They are being targeted in a way that can utilities or municipalities work in sync with each other to reduce that evening demand and having more reliable system coming into the, specifically water pumping. If water needs to be pumped to fill up in those overhead tanks to be supplied to the city, can it be done at a hour when it is kind of an off-peak hour? And so those kind of schemes are also being tried a lot. Having said all that thing, and it all looks good, issue with DSM is it is not so easy to scale. One is, as I already talked about, is the infrastructure requirement. You need to have very good infrastructure because you need to have smart meters, you need to have a smart grid kind of a system, you need to have good softwares to handle these things, you need to have good economic models. So overall, while this is an interesting tool to have, this is not such a intuitive tool to handle, and this is not a tool which will work on it itself. It needs really a good working at a background level to implement this thing. What it can lead to is that if you're not careful, it can give a signal of distorted tariffs and subsidies, which will overall weaken the price signal. So this is something which can lead to a situation where overall price signals can be very confusing, and it can lead to a situation where you are not able to rightly implement it, or it can have an adverse impact on your overall billings also. Institutional fragmentation also limits coordination, because one body will have its own interest of rolling out this scheme, another body will have it. So for example, discoms will have their own way of looking into it, while generation companies may have their own way of looking into the whole thing. While so overall, while on the other hand, the consumption industry might be looking this from a different eyes. In industry per se, the manufacturing industry may look it from a different eye. So because of this lack of coordination, this can lead to some issues, and uncoordinated behavior can lead to a situation where you can have either unhappy customers or unhappy suppliers. So that's another thing which, so it needs a very kind of a matured, fixed kind of a system, and very transparent software based system where everybody could see what is happening and what is in it for them to make this transition. Behavioral inertia, as we all know that anything which we are used to work in a certain way, if I'm used to use my washing machine at a specific time of the day because I want my my cloth to be dried under the sun at a specific time of the day, because that's what I've been doing for years. For me to change that behavior is not so easy. So that is another. Behavioral inertia is another. It leads to slow adoption, and financing and the implementation capacity remains constant because of the, as I talked about, that it needs a very mature softwares, it needs a very mature economic modeling around the whole system to be implemented rightly. With this thing coming into picture, this is not so easy to scale, and this can lead to a situation where we can have, though it's a good scheme to have, but implementation of this overall may not be so easy. But having said that, DSM has its role in overall net zero energy transition, because it will enable higher penetration of renewable energy. If you can manage your renewable energy generation and power utilization at the same time, if you can do a kind of a management pretty well over there, it can lead to higher penetration of renewable energy. It will reduce the need of new generation and network capacity. We have talked about this point a lot, so I will not harp upon this point anymore. But you can understand that this is a huge benefit for overall net zero transition, because any new infra will not only have the running emissions, but also the embedded emissions, which will be generated during the manufacturing of the system itself. Overall system efficiency will improve, which will again reduce the carbon footprint per kilowatt hour, and it very well complements energy efficiency, but it cannot of course replace energy efficiency, because we are not talking about reduction of power consumption here, but what we are talking about is that power consumption is managed in a way that our infrastructure load is reduced. So this is where I'll end this lecture. Next lecture, where we will pick up from here, we will look into some of the, like, whatever theory I've taught you in last 3-4 classes. I'll pick up somewhere around giving you through some numerical examples. I'll try to show you and help you to understand through some of the numbers, some of the concepts that we have talked through, and then we will move to some good economic discussion also afterwards, that while energy efficiency is good, while DSM is good, what are the challenges? What it leads to some very interesting behavioral economics phenomena, and we will touch upon it as we kind of go along. Thank you.